Hello, I'm Gary Pocock, and this is my Week 3 reflection for the Physics Modelling Instruction course. This week I'm going to, first of all, talk about one topic that came up in last week's class that I've been thinking about since then, which is the adequacy of the charge diagrams that we use in describing charge distributions. Then I'll talk about, briefly at the end, I will talk about the field mapping activity and the PhET simulation activity that we did during the week. Alright, charge distributions. Now there are two main aspects of charge distributions that we discussed last week, and that was the representing polarization and also representing insulators and conductors and the differences between them. And there are lots of different ways of doing it, and it seems that none of the diagrams are going to be perfect, but some of them are potentially more misleading than others. So I thought what I'd do is I'll just have a closer look at some of the diagrams that we've seen and just weigh up the strengths and weaknesses of these diagrams. Alright, so the main issue with polarization that was mentioned last week was the failure of a lot of diagrams to show gradient of charge. And the main issue with conductors and insulators is a clear representation of bound and free electrons in the different types of materials. So let's have a look at some of the diagrams. Okay, this diagram up here is from the teacher's notes, and this is fairly typical of the way polarization is shown in many cases, where all the negatives are down one side and all the positives are down the other side. So there is a problem there in it doesn't show the gradient of charge going from most negative on the left hand side to least negative on the right hand side. There's further problems with this diagram in that there's a whole little circles here with arrows, with plus signs down the right hand side, which is a traditional symbol that we use for the fixed nuclei, so that is a potential source of confusion. And here the nuclei themselves have no symbols in them whatsoever. So that diagram has a lot of potential for confusing students, I think. Now what interestingly came up last week was that there is an alternative set of diagrams in the Chem Notes, the modelling instruction Chem Notes, and I'd certainly never seen this style of representation before, and it is certainly much more successful at conveying the gradient nature of polarization. So here we have a conductor on the right hand side and a large positive charge over here, and so we can see that the electrons represented by the dots inside each atom are moved to the left. So there is a high concentration of electrons over on the left hand side, and then that concentration is trailing off until there is very little on the right hand side. So that is nice. That's a good way of conveying polarization, and this is for a conductor, so the electrons are free to move. I should have shown in my pictures an unpolarized version, so that should be there first of all. So in the unpolarized version there are 3 electrons in 3 dots representing electrons in each one of the atoms, so the electrons are evenly distributed. Then the positive charge is introduced and the free electrons move over towards the positive charge, but in this gradient-like way. And then down the bottom here we've got a representation of polarization in an insulator, and in this case the electrons are still bound to the atom, so every atom still has 3 electrons in it, but they've all moved to one side. Possibly this diagram could be even improved by using the typical polarization symbol, which is distorting the atom, making it a little elongated, and so with one end negative and one end positive. I don't know whether that would help or not in this case, but that was nice. Alright, this is another representation that's in our notes. This is the official answers for worksheet 2. In this case, we're looking at unpolarized materials. The top one is meant to be a metal and the bottom one an insulator. So in this case, what the writer of these answers tried to indicate was that the electrons are free at the top here. They're not inside the atoms, so they're floating around, and whereas at the bottom they are bound to the atom. So that's one way of doing it. I think it may be okay, provided you also include a diagram in which you show the polarization and you show the electrons moving towards one end, and in the metal and in the insulator you show that the electrons can't escape the atoms, but they've all moved to one side. So you'll notice in the circles here that the electrons are distributed in different ways in each one of the atoms. Some of them are on the side, some of them on the top, some are on the bottom. So there's a random distribution, and they will all move to one side if a charge is introduced here. So that's another way. That's not too bad either, I think. Alright, now the text that I've found most careful in its representation of polarization and insulators and conductors is the Chauvet and Sherwood text. And this is an example of one of their figures. And so what you can see here is that they have used the traditional elongated molecule as a simplified representation of polarization, but in addition they've represented the strength of the polarization by the degree of elongation. So the polarization is greatest closer to the external charge, and then it's gradually tapering off through the material. So there we have a representation of the gradient in polarization, and that's really good. I really like that, and it's something I want to use in my own notes. Now here's Chauvet and Sherwood's idea for trying to display polarization in a metal. So in this case, the positive cores are represented by the plus signs. They don't use any symbols to represent the electrons. They use the colored background. So this does require color to be effective. So in this case, the blue background is meant to represent the C of, and that's meant to be C. The C of mobile electrons. And in this case, this is an unpolarized material, so the C is evenly distributed throughout the material. And then in a diagram a little bit later, we see what happens to the electron C when an external field is applied. They've represented the field by the arrows. I'd like to put a big positive charge over on this side just to make it clear what's happening. And so what we notice is that the shaded blue, which is a sea of polarized electrons, has shifted slightly to the left in response to the field. So we have some electrons over here which are not counterbalanced by, and these are meant to be on the surface of the material, which are not counterbalanced by the positives here. So there's an excess of negative charge here, and there is a deficit of negative charge over here. Hence we have this polarization in the metal. What this diagram really brings out is the very small shift that is required to polarize a metal. You don't get the misleading idea that electrons are rushing from one side to the other side in a polarized metal. So that's another really good way, I think, of representing polarization. So in summary, I would say that there is no one perfect way of representing polarization and conductors and insulators. And a variety of diagrams would seem to be the way to go. But you need to be careful, because there are some diagrams that could easily mislead students. So finally I can't resist showing a misleading diagram, and this one comes out of Giancoli. And here what we've got is insulators, and yet what they've done is, rather than showing localized charge areas, they've put negative and positive charges all the way evenly distributed through the materials, as if it was a conductor rather than an insulator, and that includes under the hand. So obviously an alert student will pick up that if it's really charged under the hand and you put your hand on it, then you're going to ground that material and it's not going to be charged anymore. So that Giancoli made a slip up there. They've got the wrong representation for charged materials that are insulators. Alright, moving on. So the first activity I did at home was the field mapping activity, and that was good. That was a very useful activity. I think students would really benefit from doing an activity like that. Just the process of going through, calculating the charges, calculating the forces, translating that into the proper scale on the diagram. It seems natural to follow up a worksheet like that with some follow-up questions. An obvious question I'd like to ask the students while doing this is, you notice that the center charge is much larger than the small charges surrounding it. Why do you think the worksheet was designed in that fashion? And it's not just a little bit smaller, the surrounding charges. They're, I think it was 10 to the minus 8 versus 10 to the minus 5, so we're talking 1,000 times smaller. So that would be a good opportunity to discuss in class test charges, why they should be smaller, and interaction between the fields of two charges. The other thought that I had about this activity was that I've got something slightly similar that I do myself, and one of the things that I do is I put concentric circles around the center charge. So this is designed to really bring out the distance relationship, so that when you double the distance, you can see from the arrows that the arrow is 1/4 the length, and when you halve the distance, it's 4 times the length, and so on. So I thought that might help bring out the force-distance relationship more clearly than just having a random spread of charges. Anyway, that was just one idea. Finally, the last thing I did was the PhET simulation, and I thought that was really good. I really enjoyed it. I love the dynamic nature of it and the way the field arrow shifted around as you move the sensor. I love the idea of calling it a sensor, and I thought that it could potentially be a really good home activity, an outside class activity, if you're trying to do things like flipped classrooms, which is something that's on my brain at the moment because it's something that a lot of people are trying to do in my area. The wording was a bit unclear in places. It really does strike me that this is an activity written for someone assuming that it's happening in class, and there's a lot of verbal clarification going on. If you wanted to make this an outside class activity, you'd really need to work on improving the directions a bit more. Just basic things like clearly distinguishing in your formatting between what's an instruction and what's an actual question. And I've got a few other reflections that I submitted with that particular worksheet. And what have I got? Half a minute. Just finally, this is going back to the diagram situation. I can't resist looking at this. This is the answers to worksheet 2 that we discussed in class last week. And one of the issues that came up was, we're here, so looking at question 5, we're looking at pi plates here. Here's the Van de Graaff generator, and here's pi plates. And this is meant to be the distribution of the pi plates. Now, I'm pretty sure that this distribution here is not quite right, because pi plates are solid, and I reckon that the charge distribution is going to be throughout the solid material. So that's just an example of how you can easily get tricked up by 2D diagrams.